In this lesson, we're going to look at graphing vectors in three-dimensional space. Let's start by looking at vectors in three-dimensional space. So vectors in 3D. Let's move that up. If we have a point in three-dimensional space, let's say this is point 1, it has a location for both x, y, and z, and this is a triplet. We've got x sub 1, y sub 1, and z sub 1. So there's our first point. And then another point, point 2, that is x sub 2, y sub 2, z sub 2. So our point is going to start at P1 and end at P2 in three-dimensional space. Now there are two ways that we can write our vector. The first way we can write it is in component form. And in component form, we specify the components of our vector. So component form is first. And we say that vector P sub 1, P sub 2, and we put an arrow over that to represent a vector, is equal to both an x, y, and a z component. And our x component is x sub 2 minus x sub 1. Our y component is y sub 2 minus y sub 1. And our z component is z sub 2 minus z sub 1. So let's move that up. And that's our component form. Now our next form is a linear combination form. Linear combination form, and this is a way to write our vector P1, P2. So we write vector from point 1 to point 2 is equal to x sub 2 minus x sub 1 in the I direction, and we put a little arrow actually over the I, plus y sub 2 minus y sub 1 in the j direction, plus z sub 2 minus z sub 1 in the k direction. So here we have our vector in 3D form, that is from point 1 to point 2. We've got our component form and our linear combination form. Two ways of writing out a vector in three-dimensional space. So here we have our x-axis, our y-axis, and our z-axis, and we're looking at the positive x, positive y, and positive z with our origin right at the center there. The vector represented by the directed line segment AB, and it's written this way, AB, with a vector over it, has an initial point A and a terminal point B, and a magnitude which is the absolute value, I'll put this over here, of AB. So that's our magnitude. Two vectors are equal if they have the same length and the same direction. If our initial point A is at the origin and our final point B has the components 3, x equals 3, y equals 4, and z equals 5. And let me fix that, that's b. We can graph it here. So here I come out 3 units from the x-axis running parallel to the y-axis, and then I come out 4 units on the y-axis running parallel to the x-axis, and I have a point in my xy plane. Now I go up in the z direction, and I end up at this point right here. This is the point in 3D space, and it is the point 3, 4, 5. So let's put that in there. 3, 4, 5. X is 3, y is 4, and z is 5. So with our initial point A at the origin right here, 0, 0, and our final point B at 3, 4, 5, we draw a vector from our initial point to our terminal point, and we're going to have vector AB. So here's our vector AB in 3-dimensional space. Now let's label point A. This is A. I'm labeling it in green. And I'm going to switch to blue to label point B. And then I'm going to go back to green, and I'm going to label this point right here. Let's call this point C. And our point C is actually in two-dimensional space. It is x is 3 and y is 4. That's the point C. So I didn't put a z value in, it's 0, but if I'm looking in this plane here, this x, y plane, and I'm just looking at this two-dimensional space, what I have is I have another vector, and this is vector AC. So let me draw that down there. Here's vector AC, and it's in the two-dimensional xy plane. And so when we talk about vector AC, this is two-dimensional plane, where AB is in a three-dimensional plane. And we want to write it in component form. Vector A, we use triangle brackets on each side, and we put in three-dimensional space for vector A is 3, 4, 5. And then two-dimensional space for vector C is merely 3, 4. So that's how we would write our vector in component form, where we have our x component, our y component, and our z component in 3 dimensions, or our x component and our y component in 2 dimensions. So here I can say that my vector for AB is equal to vector 3, 4, 5, and then my vector AC is equal to 3, 4. I'm going to give it a subscript for that. And here I have vector AB, 3, 4, 5, and vector AC, 3, 4. So now we're going to look at finding the magnitude for each of these vectors. We can see their direction by looking in the 2-dimensional space and the 3-dimensional space. But now we want to find out, what is their magnitude? How long are they? So now we're going to find the magnitude of a vector in 2 dimensions. If we start with a vector v, and it's in 2 dimensions, we can write it in component form by putting in its 2 components. Let's say v in the x direction and component of v in the y direction, z direction. Let's fix that. In the y direction. Okay, let's move that up. So if we want to find the magnitude of the vector, well, first of all, we write the vector, and we put the magnitude symbol around it, and what it's equal to is the square root of the sum of the square of the two components. And it's written like this. So that's the formula for finding the magnitude of a vector in 2 dimensions. So with that information, we're going to find the magnitude of our vector AC. And that's equal to the square root of the x component, which is 3, squared, plus the y component, which is 4 squared. So we end up with the square root of 3 times 3 is 9, 4 times 4 is 16. So it's the square root of 25. And the principal square root of 25 is 5. So the magnitude of vector AC, which is in 2-dimensional space on our xy plane, is 5. Now let's find the magnitude of a vector in 3-dimensional space. So we'll start with our vector v, and we'll write it in component form. We have vector v's x component, vector v's y component, and vector v's z component. Let's move that up. So to find the magnitude of vector v in 3-dimensional space, we're going to take the square root of the sum of the squares of the individual components. So we'll have that our x component squared plus our y component squared plus our z component squared. Okay, so with that information, let's find the magnitude of vector AB, which is in 3-dimensional space. So that means that we're going to take the square root of all 3 components squared, so 3 squared, plus 4 squared, plus 5 squared. So we end up with the square root of, well, we know 9 plus 16, well, I'll write it down, 9 plus 16 plus 25, and that's going to be the square root of 50, which can be written as, let's write it down here, well, we'll squeeze it in, 5 radical 2. So 5 times the square root of 2 is the magnitude of vector AB in 3-dimensional space. Now imagine we have a vector v. It is not equal to 0, so it is a non-zero vector, and it's in 3-dimensional space. Then, if we take that vector v and we divide it by the magnitude of v, then what we get is a unit vector. This is a unit vector in the direction of v. So this is a unit vector. It's a vector that has a magnitude of 1 unit. It's a unit vector in the direction of vector v. Then we can say that the vector v itself is equal to its magnitude times its unit vector, which is v over the magnitude of v. And you could see by canceling out the magnitude of v, we'd have vector v. But this expression right here, this expression is the vector v, and it is a product of vector v's length or magnitude and its direction. So now we are going to try this in example by expressing the vector 2i, 1j, negative 2k as the product of its magnitude and its unit vector. So the first thing we'll do, is we're going to find the magnitude of v. So here's our vector v, and its magnitude is the square root of 2 squared, that's from the I component, plus 1 squared, that's the j component, plus a negative 2 squared, which is the k component. And that's equal to the square root of 4 plus 1 plus 4, which is the square root of 9, which is equal to 3. So the magnitude of v is equal to 3. Now let's find our unit vector, and our unit vector is vector v divided by the magnitude of v, which we just calculated to be 3. So it's equal to 2I plus j, and there should be arrows over these, minus 2k, that's our v vector, and its magnitude is 3. So if we separate these out, we have 2/3 in the I direction, plus 1/3 in the j direction, minus 2/3 in the k direction. So now we express the vector v as a product of its magnitude and its unit vector. It is 3 is the magnitude, and its unit vector is 2/3 in the I direction, plus 1/3 in the j direction, minus 2/3 in the k direction, and this is the answer to this question. This is vector v expressed as the product of its length and its direction. Now we're going to find the vector that has a length of 1/2 and a direction 3/5 j plus 4/5 k. So we know that vector v is equal to its magnitude times its direction. So v, there's its direction. And its magnitude is 1/2, and its direction is 0 in the I component, 3/5 in the direction of the j component, and 4/5 in the direction of the k component. And so that works out to be, well, 1/2 times 0 is 0, so 3/10 in the j direction, plus 4/10 in the k direction. That's in component form, so this is one way to express our answer. And another way to express our answer would be to say that v is equal to 1/2 times, I'm going to write this in component form, 0 in the I direction, 3/5 in the j direction, and 4/5 in the k direction. And we can write this as 1/2 times 0 is 0, 1/2 times 3/5 is 3/10, and 1/2 times 4/5 is 4/10. So this is the other way that we can write this. Let's put a box around it. So 2 ways to write our answer: in linear combination form, which is our first form, or as written in component form. Okay, the next thing we're going to look at is the midpoint. This is the midpoint of a line segment. So midpoint, and we're going to call our midpoint MP of a line segment, and it has to be a segment because it has to have endpoints so that we can measure it in order to have a midpoint. So the midpoint of a line segment, and that'll be line segment P1, P2, starting at P1 going to P2, such that P1 is the point x1, y1, z1, and P2 is the point x2, y2, z2. And here's the formula for midpoint. It has an x, a y, and a z coordinate. It's the sum of the x coordinates from P1 and P2, cut in half. And your y coordinate is the sum of your y coordinates from P1 and P2, cut in half. And then the sum of your z components from P1 and P2, and that's also cut in half. And there you have it. That's the midpoint formula. So here we're going to find the distance between P1 and P2 given points P1 and P2, the direction of the vector, and the midpoint of the line segment formed by that directional vector. Let's start with finding the distance between point 1 and point 2. So to do this, we put it in component form, and then we take the square root of the square root of the sum of the square of the components, and we get the square root of 50. And that simplifies to 5 radical 2. This is the magnitude of the line segment P1, P2. Now we're going to find the direction of vector P1, P2. Again, we put it in component form. We already know what the magnitude is. And the directional vector is basically the magnitude times the vector. So here we have it in component form. Now we find the midpoint of the line segment formed between these 2 points. And the midpoint is the sum of the x-coordinates, -1 and 2, are added together, cut in half. That gives us a 1/2. The sum of the y-coordinates, 1 and 5. 1 and 5 is 6, cut in half. That's a 3. And the sum of our z components, 5 and 0. 5 plus 0 is 5, cut in half, is 5/2. And this is the midpoint of P1, P2.